I think you'll find it interesting as well, though. Basically, what we're going to start talking about is the physical characteristics of computer memory because we already talked about these a little bit, but we have some motivations that we need to understand that we're going to be talking about in the next few lectures. So we need to understand exactly how computer memory works, or at least at a high level. So we have two memory areas in our computer. We have the registers, which are sort of formally known as the register file. Very small number of addressable locations. IA32 has 8 of them. In fact, the processor will have many more because it can do all kinds of fancy instruction reordering and register renaming and all of that kind of stuff. But hey, we can think of it as being 8 because that is the abstraction it presents. And then we have main memory, which is much, much larger, and RISC has these load store operations for accessing memory, and CISC allows you to directly encode addresses or indirectly use addresses from registers in your instructions as well. So you can see that there's various ways of accessing it. And we sort of expect that registers are probably going to be faster. We saw that the load store logic has to be involved if we're reading from memory. And so, and if we're doing CISC, then we know that there's some kind of address computations going on. So clearly that's going to make it a little bit slower than just using registers. And of course, data alignment is a thing as well. We have to think about data alignment when we interact with main memory. Registers, we don't really have this problem because it's just one cell. You have to access it in an aligned manner. So in practice, what we're going to be looking at is the fact that small memories tend to be faster than large ones. Particularly if you hold the technology constant. If the technology is constant and you have a small memory and you're comparing it to a large memory, the small memory is going to be faster for physical reasons. And also, larger memories tend to be denser than small ones because who wants to make a really giant memory with some technology that doesn't have a very high density? And as you increase the density, that also affects the speed of access. The speed of access actually goes down as well. If you only had one technology for storing information, then you would use it. But we have several different technologies, and so we use the larger, slower, denser ones for doing this larger data storage. The number one thing that affects our ability to access memory quickly, and for any circuit to go quickly, is just the amount of time it takes for signals to propagate down a wire. And you may or may not know who Grace Hopper is. Who knows who Grace Hopper is? Good. You who don't, look her up. Like right now would not be too soon. She was a really important person. I think she wrote the first compiler too. She helped develop COBOL, I think it was. And she would always, when she would go around and talk to people, she would have 1 foot long wires. And she would say, here's a nanosecond, because that's how long it takes for a signal to travel down a foot of copper wire. And so she would hand these out. And so you can see that if I make a circuit small, then I can make it go faster than if it's large, just because signals take time to propagate down wires. And this is partly why chip vendors want integrated circuits to be as small as possible. And so they continue striving to manufacture these circuits as smaller and smaller, and that'll allow them to be faster, consume less power, and so forth. So it actually improves a number of things. Now, gates are even slower. There's a propagation delay associated with gates, and anybody who's taken EE50, do you guys talk about it in 51 or 52? Remember? 52. 40. 40 is a thing that didn't exist when I was an undergrad. So, okay. Do CS majors take EE40 or not really? Okay, so maybe 52 is your only exposure. Sounds like 40 is a great one too. But these signals take time to propagate through gates. Gates take a while to settle down into a stable state. And so, given that that's the case, the more gates or the more logic you have to propagate a signal through, the slower that signal is going to make it through. And like I say here, there's a few other constraints here. So the longer a wire you have to drive, the longer it's going to take for the gate to go stable. And the more things that a gate has to feed, the longer it's going to take for that gate to become stable as well. So it adds up. It takes time. And so these things slow down our circuits. And these limits are affected by temperature. Obviously, if we can make it really, really cold, and usually you'll see this in people who are, they love trying to overclock their systems, and they're like, I dipped my computer into liquid helium and I ran it at like 14 gigahertz or something like that. So the slower this, the cooler the circuit, the faster it can go. The hotter it is, the slower it will go. Okay. Now, those are all physical constraints. We're going to look at a few other things now that we understand that these things slow us down a little bit. We're going to pretend that we're building a memory just out of memory cells and multiplexers and demultiplexers for addressing. Very simple. It's not anything super complicated. Like I say, a fixed size component for accessing memories of different sizes, and we'll ignore how we actually store individual values. So let's say that we had a 4-cell memory. So we can store 4 bits in this thing. And we can address those bits using A0 and A1. And you can see that that demultiplexer allows us to store a bit into whichever cell we want, and then the multiplexer can be used for pulling data out. Now, I don't want you to get caught up in how we implement this. Yes, it is kind of dumb. But what I want you to look at is, here's the 4-cell memory. Now, let's upgrade it to 16 cells. And you can see that something happens, right? We've increased the complexity of our addressing logic, because we have to. We have more cells that we need to address. And guess what? When we propagate through those things, it's going to take more time. And so as we scale up our circuit, our memory circuit, we have slower and slower addressing that we have to perform. Okay, so like I say here, we can assume that the memory's cost is the addressing logic plus the cell logic, and we can pretend that the cell logic, looking up a value or storing a value into that cell is going to be constant because the cells themselves are not changing as we change the memory size. But the addressing logic definitely does change as we increase the memory. So how would we approximate this time complexity type thing? For n cells, it would be what? Yeah, log n. Exactly. Plus, times some constant, obviously, but we'll just throw that in there. So you can see that as we grow our memory, holding the technology constant, we are going to see slower access times. Now we also have to lay these things out on a 2D surface. We're getting more and more clever in how we do this, so we are seeing improvements in various ways. But we want to try to pick a layout that's, for example, not a single long line of cells, because that would probably be dumb. And so let's say that we choose a square. And so again, we have the logic of looking at a particular memory cell. That includes both the addressing logic and the cell access time itself. But then we also just have the time for the signals to propagate down the wires. And so like I say here, T logic includes the log n term, and T wire is the signal propagation times. So again, for n memory locations, what is that going to be proportional to? Presuming a square layout. Yeah, square root, right? Because that's going to be how long the side is. Okay, so square root of n on both sides. So again, we have some constant times square root of n. So this is basically what we're up against. We have the C1, which is the, what do I have here? Yeah, so I have multiplication in here. So C3 is the cell access time. That's the one that's just constant and it doesn't really change. So we're not changing the technology. But as we increase the size, you can see that the addressing logic adds in a component, and it gets larger and larger as we increase the size. And the propagation delays just down wires is increasing as well. And so this is the thing that makes us a little sad, that we basically can't access large memories at the same speed that we can small memories. Small memories are always going to be faster. So where we want to have really high performance, we need to have tiny memories. That's another reason why we have a register file on the processor. And we load stuff from main memory and we work with it in the register file, because that thing is going to be super fast for the processor to access. And it can keep it right next to the ALUs and the addressing logic and all of that other stuff, so that it's really fast to pass the values across. Now there's a lot of different storage technologies. We're going to go through quite a few of them. The one that we do not include, which makes me sad, is solid state drives. Who's got solid state storage for their disk now? Yeah, like most of you, I think, well, over half of you put your hands up, and the rest may just be lazy. I do now. I just thankfully got a new laptop, and I have integrated circuits now. There's no moving parts except for the lid on the laptop, I suppose. You have volatile memory. Volatile memory loses its state when you remove power. That's why we call it volatile. Non-volatile does not lose its state when the system is powered on. You have static RAM and dynamic RAM. Now, examples of non-volatile memory would be read-only memory. You have a couple of different kinds of read-only memory. You also have electrically erasable programmable read-only memory, EEPROM. Okay, that would also be known as flash memory. And then you also have magnetic disk storage. So we're not going to really be talking about the electrically erasable programmable read-only memory, even though it's really valuable to understand. In fact, flash drives add all kinds of complications to the way that these computer systems work. We talk about those a lot more. We spend a couple lectures talking about them in the OS class just because of the complexities. So static RAM. RAM just means random access memory, which means that I don't pay any greater cost for accessing something far away than accessing something right after the thing I just accessed. So like I say, any data value can be retrieved in constant time. And the reason why we call it RAM is the other major form of storage back then, when these things were being developed, was magnetic tape. And that was sequential storage, because if I wanted to access something 10 megabytes away from where I was currently reading, I have to, run the tape a whole bunch before I can get there and read it. But if I want to read the value right next to it, it's super fast. So random access memory, it's also known as direct access memory because I can specify an address and directly retrieve that value. Okay, so static RAM has bistable memory cells. They can either be 0 or 1. And the state will not change as long as power is applied. So this is nice. It's going to maintain its state. This is the idea. This is not the way SRAM cells are implemented. So if you're a memory geek, then don't freak out because I understand. This is an example of a D flip-flop, and it illustrates the concept of how these SRAM cells work. Basically, you have some gate whose output is fed into the input of another gate whose output is fed into the input of the first gate. So that you can have a feedback. And that way the gates can enter into a stable state. And then you have additional logic to allow you to switch that hookup, that setup, from one stable state to the other stable state. Okay. D flip-flops are nice just because they have a data input, and if you clock it, then it will store the data input, and it will maintain that until you clock it again with a different data input. Okay. So that's why I like that one as an example, but it's certainly not the most simple flip-flop. SRAM cells, if you only have one output, are going to require just 6 transistors. We're pretty good at building these things. I think it adds like 2 transistors per output that you want. So for example, the register file where I have these 8 memory locations, and I'd like to feed one register into one ALU, or one side of the ALU and the other register into the other side of the ALU. Obviously, I'm going to require more transistors to build that, but very small. And we have a layout like this, and you'll notice that we feed, this is crazy, this is an 8-bit wide SRAM circuit. 8-bit wide with 8 cells. So this is basically exactly like our first memory that we talked about in the first week. And you can see that we address this with 3 address lines since we have 8 cells, and the individual cells maintain their state. When we are ready to access something, we send the entire address to the decoder. That actually becomes important in a second. Note that we send the entire address in one shot to the decoder. Okay, then that activates the particular row that we want to read or that we want to write, and then we can either read values and send them out on the data lines, or we can take the data lines and write them into the cells. Okay? So that's static RAM. That's really simple. In this context, these horizontal lines are called word lines because you can see that it activates the entire word at once. In this case, our word is 8 bits. Okay. The vertical lines are called bit lines because you can see that, for example, the second line from the left is going to be the second bit for all the words in the memory. but we activate a particular word line, and then that's going to be the second bit of the word that we activated. Okay, so that's why we have word lines and bit lines. Now SRAM is cool. We like it because it's fast to access, takes up a little bit more power, but these little cells with 6 transistors apiece do take up a little bit of space, and so there's only so much static RAM that you can actually fit onto a chip. And so there are other circuits that are sometimes used. In fact, there's one that's used very heavily, and that one would be dynamic RAM. What does dynamic RAM use for storage? Yeah, it just uses a single capacitor. The capacitor is either charged or discharged, and that is how we store information. Okay. Now we also need a transistor so that we can actually activate that cell. So we need to be able to turn it on or turn it off so that we can read whether or not the capacitor is charged. Of course, if we have a capacitor storing our information, what do we quickly notice? Yeah, the capacitor's charge goes away, and then we're sad because we lost our information. So that's why it's called dynamic, because it knows the state right now, and then shortly after that point, it will forget it. So you have to keep reminding it of what it knows. We call that refreshing it. So we have to sort of tell the DRAM, okay, DRAM, this is what you're storing here, this is what you're storing here, and that way it'll actually remember. Okay? And it turns out, it's very nice. There's easy ways of causing DRAM to refresh that take very little effort, and so DRAM circuits are very popular, and therefore they're very ubiquitous as well. Like this laptop has 16 gigs of DRAM on it, and I imagine that probably all of you have large amounts of DRAM at your disposal as well. Okay, let's see. Yeah, so you can conceptually think of it in this way. It doesn't exactly work like this, but it's pretty close. Okay, we have a transistor that allows us to see what's on the capacitor, and like I say here, when the transistor is activated, then that allows the capacitor's output to go somewhere. Or it allows us to write to it as well. Now the thing about DRAM, remember SRAM gets the whole address in one shot. DRAM actually gets the address in 2 parts. And this actually allows us to reduce the pin counts. So we reduce the number of pins the device has to have on it. And it also allows us to have a very large amount of memory on the DRAM cell that we can then address. So like I say here, typically the memory is square. And so we have this in 2 phases. First thing is we have to specify a row address, which tends to be half the address bits that we normally would use to address the DRAM cell anyway. So row address is half of the address bits. We tell the DRAM, hey, here's the row address. Then we say, here's a column address, so the other half of the address bits. And then we tell the DRAM again, and that's the point where it reads or writes. This is a very simple DRAM circuit, particularly because there's no way that we could actually have like an 8-bit wide DRAM circuit and actually show you what that would look like on a slide. Okay? So this is actually a 1-bit word size. You can see, so it's funny because you'll see 4 cells along each one of these rows. That doesn't mean that we have a 4-bit wide DRAM. We only have a 1-bit wide DRAM because we have a row and a column address that we have to specify, and then that selects this thing that's normally called a supercell because it has multiple bits in it. But in our case, it's just a cell because we only have 1 bit. Okay? So we have 4 by 4 here. And so you can see that the address lines, we only have 2 address lines, but we actually effectively can address up to 4 bits. We can use 4 bits of addressing because we feed in 2 bits for the row latch and then 2 bits for the column address. Okay. Let's see. Yeah, so horizontal word lines, vertical bit lines. Although in this case, we're only seeing 1 bit line, and the word line, basically you can think of the word line feeding each cell because we're activating a whole row, and a whole row will activate multiple cells. If this was a 16-bit wide memory, we would be activating 4 16-bit values. Okay? So just make sure you keep that all straight. So the first thing we do is we send in half the addresses, half the address lines. We activate the row address strobe. So if you've ever seen RAS and CAS on memory circuit descriptions, or especially if you're on a website buying memory for your computer and you see RAS and CAS, this is what they are. Row address strobe latches in the row address. So A0 and A1, those values are stored. And you can see that all of the rows on that row address are activated. Okay? So we're actually activating a whole bunch of memory cells that are all next to each other. And what happened is kind of really interesting. Those things are sort of connected to the wire. So the transistors are activated, and so the capacitor's charge is allowed to bleed out, and it goes into an amplifier that then sort of pushes it in whatever direction the capacitor says it has. So if it has no charge, it pushes it to 0. And if it has any charge, then it pushes it to 1. And what that does is it also has the side effect of pushing charge back into the capacitor. So reading it refreshes the value. That's pretty awesome. Okay, this all happens automatically. So that bit sense amplify plus latch, it has a lot of stuff going on. And if you read about how DRAM works, you'll get a lot more of the nuances and the details. It's pretty awesome technology that they were able to figure out. Okay, so we bleed that charge onto a line. An amplifier sees how much charge came and pushes it to 0 or 1, and that causes a feedback to the cell, and it recharges it. Okay, so that was the row. Remember, the entire row of cells is now activated, and that entire row has been brought down into the bit sense amplify plus latch part. But we now need to figure out which of those words do I actually want to read. And so the column address is specified, then CAS is triggered, and that latches the column, and that selects the specific column that I want to read. Okay? And if we had a 16-bit memory, we'd get 16 bits coming out. But since the slide is small, I can only have 1 bit coming out. Okay? So you can see that the value is actually read out of the latch at this point. Okay? Any questions? You can already see that's a lot of work just to get a freaking value out of a memory, right? Static RAM is a lot simpler, and it's also a lot faster. We have simpler addressing. We have fewer steps to go through. We're just like, hey, here's an address, and it says, okay, here's the value. Here we have to like jump through hoops to get the thing out. Okay, so like I say, here's 16 1-bit DRAM. Typically, you'll have 8 or 16 capacitors plus transistors per memory cell. I already talked about this before. And so the column address selects, like, so that those vertical lines, you would have a little slash across them to indicate that they were little buses carrying 16 values down or 8 values down or whatever you might have now. So since there's so many steps involved, you can imagine that processors don't really want to deal with this directly, because that increases the complexity even more. Okay, because we have all these steps that we have to go through. We also need to periodically refresh the DRAM, and there's a really easy way of doing that. I think I talk about it here. Maybe I don't, but basically, I think it's on a subsequent slide. All we really need to do to refresh the memory is put in a row address, activate RAS. That activates the entire row. That refreshes the row at the same time using the mechanism that I already described. And we don't have to do anything else from there. We could just go on and periodically do the next one, and the next one, and the next one. And that'll refresh each row in sequence. We never have to activate CAS. So you can imagine that something's got to go through and do that. Periodically make passes through the memory to activate these things. So that's where a DRAM controller comes into the picture. So the processor just says, I want to read this address, and the DRAM controller takes care of, okay, row address, RAS, column address, CAS, get the value out and pass it back. And then it can sort of say to the processor, here's your value, I finally have your value. Okay? And it also traverses DRAM periodically using the mechanism I just described. So you just set a row address, toggle RAS, and it will refresh that entire row. And like I said, you don't need to activate CAS. So it's basically half the speed of a memory access. Okay? Now there are a few processors that include DRAM controllers on chip. But it is risky to do this, and the reason why is because there's a lot of different variations on how DRAM works. You have various optimizations that are employed, and so forth. And so if you wanted to upgrade your system to support a new kind of DRAM, you're stuck if it's on the processor. You'd have to throw out the processor and get a new processor that does support that. And so in general, this is why our general purpose computer systems typically will have something on the motherboard that handles DRAM interaction. It won't actually be on the processor itself. Let the processor do what it's good at. Let something else handle the DRAM access. Okay? Here is an example. You have what's called fast page mode DRAM. You may have noticed that when I activate the row address strobe, I turn on an entire row of memory cells. Remember, it's not a 4-bit word that we're talking about here. It's a 1-bit memory. We just happen to activate 4 cells that are right next to each other. And so if we have like, rows that contain 10 cells or 16 cells or something like that, if I activate all those things, I'm turning on all 16 of those cells, and all 16 cells go down into my latch. So if all those things are latched, why would I read just one of those and then throw away the rest of my work? That seems like a waste. And so this is a pretty common optimization because it's very, very useful. Most programs access things in sequence, so why not take advantage of it? So fast page mode is, I put in the row address, I activate the row address strobe, that whole row goes down into the latch, and then I'll just feed column address, activate cast, get that value out, then feed in another address, activate cast again, get the next thing out. So I can just read a whole sequence of values out of my latch because I'm just reading all the things that were in that row that was activated already. That's fast page mode. Okay? A page being all the things that were activated in that one row. Okay? Does that make sense? It's a pretty useful technique. Now, it's been a while since I've updated these numbers. I think it's been about 3 years, so hopefully they're still reasonably accurate. But SRAM is quite fast because it is actively pushing data out on lines, and the addressing is simpler and so forth. So you have SRAM access times 1 to 10 nanoseconds, pretty common. DRAM 30 to 100 nanoseconds.
Including like going through the bus on the motherboard?
No, this is just the chip, the device itself. So like if you got a, I want to go find like a 512 kilobit SRAM chip, and I look at the data sheet for it, it'll say this is how long it takes to access it. So these memory cells, what we will do when we talk about modeling computer systems is that we'll pretend it also includes propagation down wires and so forth. We'll just wave our hands because it turns out it's very difficult to actually simulate or estimate the actual performance of memory caches and so forth. But yeah, we'll get to that in the future. So yeah, SRAM memory cells, they actively drive their data lines high or low, and DRAM, you have that whole thing where the capacitor sort of bleeds its charge out, and then the amplifier has to detect what that is, and then we have to latch the result and so forth. So there's a lot more steps that have to occur in DRAM, which makes it slow. SRAM gets the address all at once, whereas DRAM gets it in 2 parts, and SRAM doesn't have any refresh costs. DRAM refresh does add a little bit of overhead. It might be like 3 to 5% overhead. Maybe less now. We may have better technologies. But as we make these things smaller, they probably lose their charge faster as well. Just as a little anecdote, back when I started using computers back in the x86, like XT and AT days, 8088 and 8086, you could actually control the DRAM refresh from software. And in fact, I think it might have been done in software. I can't remember. But anyway, it was really, really slow. And so since you already didn't have very much performance to work with, my processor was like a 4 or 5 megahertz processor, you could actually turn down the refresh rate on your system and it would get faster because it's refreshing less often, you're doing that work less often. And so what we would do is we would turn it down until our system started forgetting things, and then we'd back off a little bit. We turn it back up and okay, that's a good, now it's optimized, I have my computer slightly faster. But now it's all done in hardware, so the processor really doesn't have to deal with that kind of stuff. Okay, yeah, so DRAM is much denser than SRAM because you're able to represent memory cells much, much more efficiently with much fewer components than you did with SRAM. Okay, so like I said here, 1 transistor plus 1 capacitor versus 6 transistors. And so you can scale up DRAM much more easily. And so what that suggests is, well, we really should use these things for different purposes in our computers. Okay? We'll use SRAM on the processor, because who wants to do DRAM refreshes on registers? That seems silly anyway. And then we'll use DRAM for doing really large memories so that I can have 4 gigs or 8 gigs or 16 gigs on my system. Okay, but we do have this question. How do we make it fast? Or are we stuck with the slow performance of DRAM? Now, any questions about SRAM and DRAM? All right, so the next thing we're going to talk about is disks. And by disks, I mean spinning magnetic disks. So, platters of rust that are spinning super fast in your computer. Or not so much anymore. Now they're more relegated to servers that have a lot of data to use. And even solid-state drives are becoming more common on servers, but mainly for temporary storage and so forth. So disks are comprised of platters. The platter is the thing that's spinning, just like a record player, and you have these various tracks, which is where I store my information on the disk. Okay? And you can see that each track is also divided into these little chunks called sectors. So this whole thing is spinning inside my disk drive. I have this head, and you can see here the platter is spun at a constant rate, so anywhere as slow as 5,400 RPM, which takes a lot less power. So typically you see that speed in laptop drives, although 7,200 RPM is more common now because it's faster. And then all the way up to 15,000 RPMs for super fast SCSI server drives. Okay. 10,000 RPMs is the rotational speed of the drive inside the database server we use for the database class. So 7,200 RPM, very common for desktop hard disks. Why would we vary the speeds? Well, we'll talk about that in a second. You can see that we have this arm that has a little read-write head on it, and we can slew it back and forth across the surface of the platter to actually read or write data. And so we can slew it to a particular track, and then sector goes by, and we can actually read it. Okay? And so this indicates very clearly why we want faster spinning drives. If I slew the head, and now I have to wait for that data to come by, it's going to come by a lot faster if the drive is spinning faster. So I have to wait less time for it to actually show up. Now we can add multiple platters, which is what most drives do. They'll have 3 to 5 platters in them. And you always kind of notice if you watch disk drives over time is that they say, oh, we've got an 80 gig drive. And I know 80 is small now, but just bear with me. So we have 80, and then we're going to up it to 120 gigs. And it's like, wow, we're amazing. And really what they did was they changed from having 2 platters to 3. That's really all they did in the drive. They just added another 40 gig platter. And similarly, when we get up into like 2 terabyte, 3 terabyte, they're going to just keep adding platters as well as increasing the density of the information they store. Okay. So we can add platters, and so now you have multiple heads on this one arm. And there's one on the bottom and one on the top. So you have these things sort of reading things at the same time. Now, obviously, if you have all these things on a single actuator arm, then you're going to have all of these all of these tracks that are at the same distance from the center being accessed at the same time. So all those tracks together at the same distance are called a cylinder. You can see how complicated this can get. So I can read any sector in any track in the cylinder relatively easily without having to slew the heads around. Okay? If I have to read something else in another cylinder, then I have to slew there. Okay? And I should also just mention, Old school, back in the day, like probably I can't even tell you how many years ago. But sometimes you'll read about this, especially if you take the OS class, you'll run into this in a big way. We have what's called CHS addressing. Has anybody heard of that? So yeah, that's cylinder head sector addressing. And if you look at this assembly, you can see exactly how that works. You pick the cylinder, you pick which head you want to use, and then you pick the sector of that head's track that you want to read or write. How complicated is that? Disk geometries are all really crazy. And not only that, but the amount of bits allocated for each thing, like the cylinder and the head and the sector, isn't large enough now to hold the number of cylinders and heads and sectors now that we have. And so you have another way that it's done now called logical block addressing, where it's just 0 all the way out to whatever. And so you just say, I want to access sector 831, and the drive itself figures out what cylinder, head, and sector that corresponds to. So the drives are getting smarter and smarter. Okay, yeah, so you can see that also another consequence of this approach is that further away from the center, the sectors are larger because we just have a particular angle that tells us where the sectors are. And so over time, people realize, well, this is wasting a lot of space. What would be really cool is if we could figure out how to pack more sectors around the outside of the drive than around the inside of the drive. And so now we divide them into zones, and you might have like 5 zones or 8 zones or something like that. And each zone is just a little section. So you might have a zone on the outside and then a zone just inside the outside and so forth all the way in. And each zone has its own sector layout. And the zones on the outside will have more sectors than the zones on the inside. Okay? So this allows us to store more information, which allows us to pack more data onto these drives. Okay? It also, again, greatly complicates things. And so if you have cylinder head sector addressing with zones, that doesn't make any sense at all. And so this is why everybody's been moving toward logical block addressing, because it's just a simple thing. Let the drive do all that thinking for us. Okay? The other interesting consequence of this is that if you have files that are stored on the outside of the drive, they're faster to read than files stored on the inside of the drive. It's a weird thing. Okay? And so typically when we're doing performance analysis of disks, we have to think about, okay, well, was the disk mostly full when we put the data on it, or was it mostly empty? Where did that data end up? Because that'll affect the read and write performance of it as well. Okay, major factors. So first thing, I have to slew this giant arm, which if you're a bit on the surface of the platter, it is a giant arm slewing around. It's pretty tiny in real life. But how long does it take to move to an appropriate track? And it does depend on the previous track that the head was at. And so what they sort of do is they guess. They move it around a whole bunch and come up with some average seek time for a series of random seeks. But obviously if you seek to the track right next to the current track, it's super fast to go just one track over. Okay, so that's one part of it. The other part is how long does it take for the data to come around the disk and get back to where the head is, because the head is fixed in position. Okay? And you could have to wait up to 1 revolution. You could have to wait nothing at all. So typically you look at how much time half a revolution takes so that you can figure out what the average rotational latency will be. So seek time, worst case, up to 20 milliseconds. Ugh, right? So those are like really slow drives that nobody would want to buy, so they're probably really cheap. Average case is usually 6 to 9 milliseconds. You'll see even faster access on server drives that are really highly optimized. You'll even see down to like 2 or 3 milliseconds sometimes. Rotational latency is just how much time does it take for a half revolution, because that's going to be the average case. So 8 milliseconds, 4 milliseconds for a 7200 RPM drive. And you can see that as you increase the speed of the rotation, then those numbers are going to shrink. So 15,000 RPM is going to be about half that. So you might have 4 and 2 milliseconds. So given all that stuff, you can get a sense of how long it takes to read data off of a disk. And you can see, wow, this is really horrible. 10 to 30 milliseconds. Now with a modern server drive where you normally see these disks nowadays, you might have anywhere from 4 to 15 milliseconds. But we're still in milliseconds land, not nanoseconds land. So this is really slow compared to the processor. Okay. Now, the one thing I want to mention before I go on is that solid-state drives are definitely faster than this, but solid-state drives are still in the microseconds range, not nanoseconds. Our memories were nanoseconds. Our processors are nanoseconds. Our solid-state memory is tens to 100s of microseconds, and these things are milliseconds. So you can see that there's a huge performance gap between processor and disk in particular. Okay, yeah, so we have SRAM, DRAM, magnetic disks. So here's a comparison. Again, these are 2010 numbers. This is like the most tedious and boring kind of statistic to update, so I don't do it very often. But you could probably figure it out yourself. It's probably even cheaper now for hard disk storage.
Well, RAM is like a quarter of that price.
Okay, so yeah, so I probably should update these things. All right. And if you look at these things compared to processor performance, you can see that there's a huge difference. So one clock is about 0.3 nanoseconds if you're talking a 3 gigahertz processor, which mine is in this laptop. If you have a 1 gigahertz processor, then it's going to be, about 1 nanosecond. It's going to be for 1 gigahertz processor. So you can think about this in terms of scaling these things, and there's a really great research paper that goes through and scales these things up and allows you to think about them in more realistic terms. So SRAM access, 3 to 30 seconds from the perspective of the processor if each processor clock was 1 second long. DRAM access would take 1.5 to 5 minutes. That's perfectly enough time to go get a coffee. Hard disk access would take 1 to 3 years. So do we want this processor sitting around and waiting while the hard disk is being accessed? Okay. The answer is definitely not. And that actually motivates a lot of how operating systems are designed. We're going to talk about that in a week or two. So the processor is significantly faster than the memory, but it's even worse. Here's a plot. You can see it only goes up to 1998, and there's a few plots that go all the way up to 2010. I'll describe them momentarily. But you can see that processors are increasing in speed by a certain rate, and memory is increasing by a certain rate. But the CPUs are speeding up faster than the memory is speeding up, which means that there is a gap opening up between the two in terms of relative performance. Now, what's happened is this trend has continued all the way up until about 2002, and then the CPU gap has kind of leveled off a bit, more like the first part of the graph up to 1985. So it's kind of tapered off a little bit, but it's continued to rise, and memory has basically stayed at exactly the same rate of increase all the way along. So even all the way up till 2010, we're continuing to see the same increase, or I should say, increase in the disparity between the processor performance and the memory performance. So that makes us really sad. Like I see here, the gap itself has been growing by more than 50% a year. And it's probably less than that now. Maybe it's like 30% a year. But it's still there, and it still sucks for building computers. So our dream, like if we got to have a pony, then we'd love to have a memory that was the speed of SRAM, but the size of DRAM. So I'd love to have 16 gigs of SRAM on my computer system, because then I'd be able to start virtual machines and write documents and check email, and it'd be like, oh, this is awesome. Okay? But we can't really do that because of all the physical constraints that we have. We can't really do it this way. And so what we do instead is we introduce a notion of a cache that sits between the processor and main memory. This is the solution that we've used. We've used it for a long, long time. Okay? So like I say, we use some faster storage technology than DRAM, and we use it as a staging area. So when somebody accesses information, we can use that staging area. We can move some additional information from DRAM in there, and we can improve our performance. So like I say here, when CPU reads a value from main memory, we read not just that thing, but we read a chunk of information around it. And we move that whole block into the cache, presuming, of course, that the program is going to access other stuff nearby. What happens if the processor doesn't satisfy that assumption? Yeah, hey, we get a memory the size of DRAM for the speed of DRAM. Yay, right? So, but if we have a program that's actually going to be, relatively well behaved in terms of caching, then we'll see memory that's the size of DRAM and approaching the performance of SRAM. We'll actually do some math next time to see some of the examples of this. So I don't want you to just pack up right away, because once we're done here, I'm going to tell you a few things. What kinds of program behaviors will work best? You can probably guess. You'll have a great opportunity to exercise some of that knowledge or that insight on assignment 5, and then obviously how we design these